Hey there. It's late, the monitor is glowing, and if you're anything like me, you're probably waiting for a build to finish.
Or a script to run in the background. It's the perfect time to grab a coffee.
Yeah, exactly. Settle in because we are going to level up your AI architecture knowledge tonight. Welcome to the deep dive.
Glad to be here. We've got some great material to get through.
We really do. Tonight we're unpacking a stack of notes on transformer architectures. Specifically, we are tearing down a mechanism called cross-attention.
Right, the whole when encoder meets decoder concept.
Exactly. And our mission here is really twofold for you. First, we want to explore how AI models use this exact mechanism to bridge completely different worlds.
Like translating French to English or even turning a static image into a rich paragraph of text.
Yeah, bridging those gaps. And second, we're going to uncover what I think is a massive plot twist in the AI world.
Oh, it's huge.
We're going to look at the fascinating reason why the most famous state-of-the-art text models today actually stopped using this technique entirely.
It's such a brilliant architectural journey to dig into, especially for the software engineers listening who, want to really grasp the design choices behind the tools they deploy every single day.
Definitely. So to give you a high-level teaser of what we're looking at tonight, how does this compare to what we already know?
Well, we need to contrast this with self-attention, which we've covered in previous deep dives.
The internal monologue.
Yes, exactly. You can think of self-attention as an internal monologue. It's a single sequence of data, like a sentence, just talking to itself to figure out the context of its own words.
But cross-attention is different.
Right. Cross-attention is a conversation. It's what happens when two entirely separate sequences need to communicate with one another and find common ground.
Okay, let's unpack this conversation. But before we get into the weeds of how these sequences talk, we should probably do a quick refresher on the architecture that started it all.
The original 2017 attention is all you need setup.
Right. That original transformer wasn't just one big monolithic block. It was split into two distinct halves. You had the encoder and the decoder.
The reader and the writer.
Yeah, you can think of the encoder as the ultimate, highly focused reader and the decoder as the writer.
And understanding why cross-attention was invented in the first place means looking at the core problem that two-part architecture actually created.
The translation problem.
Right. Let's say you're building a machine translation system. You feed a French sentence into the encoder.
Okay.
The encoder processes that French input through multiple layers of its own self-attention, and it builds these incredibly rich, context-aware mathematical representations of the text.
So it understands the grammar, the nuances, the relationships between the French words.
Exactly. It has the full picture. But then you have the decoder.
And the decoder's sole job is to generate the English translation, right? One token at a time, moving strictly from left to right.
Right. And the decoder only has access to the English words it's already generated.
So how on earth does it know what the original French sentence actually said?
That's the gap.
Yeah, how does it connect the English word it's about to write with the French context locked away over in the encoder?
That gap is exactly where cross-attention steps in. It functions as the dedicated communication channel between the reader and the writer.
I actually love the simultaneous interpreter analogy from the sources for this.
It's a perfect fit.
So picture a French diplomat standing at a podium at the United Nations, giving a long, detailed speech. That completed speech, all those nuanced points, that represents the encoder's output.
Okay, I'm with you.
Now imagine you're the UN interpreter sitting in the soundproof booth. You are the decoder.
And your job in that booth is incredibly difficult.
Oh, absolutely.
Because you're speaking English words into your microphone in real time.
Yep.
But as you produce each new English word, what is your brain actually doing?
You're mentally scanning the French diplomat's speech.
Right. You're asking yourself, which specific part of what they just said is most relevant to the exact English word I need to output next?
You aren't just blindly remembering the whole speech. You're selectively scanning it.
Yes.
That selective scanning, that momentary hyper-focus on a specific French phrase to generate a specific English word that is cross-attention in a nutshell.
It's a great way to visualize the concept, but for the engineers listening who want to know how the data actually moves under the hood, we have to look at the mechanics.
The vectors.
Yeah.
The query, key, and value vectors.
Exactly. In standard self-attention, all three of those vectors, the Q, the K, and the V, are generated from the exact same sequence. The sentence queries itself.
But cross-attention is different. The notes call it asymmetric origins.
The asymmetric origins, yes.
So if we have two different sequences here, who is holding the query and who is holding the keys and values?
In cross-attention, the query comes entirely from the decoder's current state.
Okay.
Think of the query as the specific question the decoder is asking. It's saying, given the English words I've generated so far, what kind of information should I be looking for next?
But the keys and the values don't come from the decoder.
No, they come directly from the encoder's final output.
Let's make this concrete. Let's use the filing cabinet metaphor.
Go for it.
Imagine the encoder's output is a massive room full of filing cabinets. The keys are the labels printed on the outside of the cabinet drawers.
Helping you find what's relevant.
Right. They tell you what kind of information is inside. And the values are the actual documents, the rich context, sitting inside those folders.
And the beauty of those cabinet labels is that they're mathematically fixed once the encoder finishes reading.
So the decoder walks into the room holding its query.
Yes, and the query is compared against all the key labels on the filing cabinets.
Now, we've talked about how this looks conceptually, but under the hood, how is the model actually calculating where to look?
The math part.
Yeah, because we see a lot of formulas with dot products and softmax functions in the documentation. But what does that actually mean for the system?
Instead of reading the raw math, think of it as a matching game.
A matching game.
Right. The dot product you see in the equations is just a mathematical way of asking, how similar is this decoder query to this encoder key?
Oh, I see.
The system runs that comparison and produces a set of raw similarity scores. Then, the softmax function takes those raw scores and forces them into percentages that add up to exactly 100%.
Ah, so it creates a probability distribution.
Exactly.
It basically tells the decoder, pull 80% of your context from this drawer, 15% from that drawer, and ignore the rest.
And then it takes a weighted sum of the actual documents, the values.
Right, to figure out exactly what it needs to know to generate the next token.
What's really fascinating is how beautiful this process becomes when you visualize those percentages.
The alignment matrices.
Yes. If you take those attention weights and plot them as an alignment matrix, the magic of cross-attention becomes visible to the naked eye.
You put the source tokens, let's say the French words, on the top axis, and the target tokens, the English words, on the side axis. Let's use the example from the notes. Say you're translating Le Chat Noir to the black cat.
Classic example.
If you plot the attention weights during that translation, you get this roughly diagonal line across the matrix.
Right, because when the decoder is generating the matrix lights up showing it's paying the most attention to low.
And when it generates black, the brightest spot on the matrix points to noir.
It's a neat, mostly diagonal alignment because French and English share a somewhat similar word order.
But that matrix gets wild when you change the language families.
Oh, completely. Consider translating from Japanese to English.
Because Japanese syntax is quite different.
Right. They typically place the verb at the very end of the sentence. English places the verb in the middle.
So what happens to the matrix?
If you look at the alignment matrix for a Japanese to English translation, that diagonal line completely disappears. Instead, you see a complex, scattered pattern.
Because when the decoder gets to the middle of the English sentence and needs to generate the verb, it literally has to jump to the very end of the Japanese input sequence to find the relevant context.
Exactly. Or think about German, where verbs are often pushed to the end of a subordinate clause.
So the cross-attention mechanism allows the decoder to just reach across the sequence and grab exactly what it needs, no matter where it's located.
And this was a massive breakthrough for the field.
Because older models couldn't do that.
Right. Before this, older machine translation systems had to rely on completely separate, rigid alignment models. They struggled terribly with long-range dependencies.
If the verb was too far away from the subject, the model would just lose track of the context.
Exactly. Cross-attention eliminated all of that overhead. It gave the model direct, instantaneous access to any part of the input, regardless of how far apart the words were.
That structural freedom is incredible.
Yeah.
But for the people actually building and running these systems, the engineers listening, how does this impact hardware?
The compute implication.
Yeah, let's talk about that, because jumping around a matrix like that sounds computationally expensive.
It does add significant computational costs, but there's a brilliant optimization built into the architecture.
Okay.
Because the encoder processes the entire input sequence up front, it only ever has to run once per task.
Oh, right. So you don't have to reread the French sentence every single time you generate an English word.
Exactly. Once the encoder runs, its output. Those rich representations are fixed.
So you can cache them.
Yes. You pre-compute the keys and the values for the entire input sequence and cache them in memory. This is what we call the KV cache, and it's crucial.
So during the generation phase, as the decoder produces token after token.
It's just calculating a new query for its current state and doing a quick matrix multiplication against the cached pre-computed keys and values from the encoder.
That caching mechanism must be huge for efficiency. But doesn't holding all those keys and values in memory create its own bottleneck?
Oh, absolutely.
I know managing the KV cache is a huge talking point for engineers deploying AI today.
It is arguably the defining bottleneck of modern AI inference. As your context window grows, the memory required to store those keys and values scales linearly.
Wow.
In a traditional encoder-decoder setup, you're caching the KV states for the entire input sequence. However, because the encoder's output is static, you can batch your generation tasks incredibly well.
So multiple different decoders can theoretically query the same cached encoder states if they're working from the same prompt.
Precisely. And it's doing this at every single layer of the neural network. You have these cross-attention blocks stacked on top of each other.
Right. The notes mention that the early layers might learn very simple, literal word-level alignments like mapping chat to cat.
Yes, but the deeper you go into the network, the layers start learning highly abstract meaning-level correspondences.
It's not just mapping words, it's mapping underlying concepts.
It's a profound architectural achievement, and it ushered in what we might call the golden era of the encoder-decoder architecture.
Oh yeah, some of the most influential heavyweight models in natural language processing history were built squarely on this foundation.
Let's list some of those power players.
You have T5, the text-to-text transformer from Google. They framed literally every NLP task as a text-to-text problem.
Right. Summarization, translation, classification.
All of it relied on the encoder, reading the input, and the decoder using cross-attention to generate the answer,
Then you have BART from Facebook,
which corrupted text and used cross-attention to reconstruct the clean original.
and MBART, which took that same idea and scaled it across 25 different languages.
Using cross-attention to build a universal meaning space where concepts from different languages could perfectly align.
Those models proved just how robust the architecture was. But then we hit the plot twist.
The massive pivot. This is my favorite part of the notes.
It's crazy when you think about it.
After all this brilliance, after solving long-range dependencies and revolutionizing translation, the industry essentially abandoned it for text. Today's most dominant household name AI models, GPT-4, Claude, Llama, Mistral, Gemeric, none of them use cross-attention.
They don't have an encoder at all.
They're strictly decoder-only architectures.
It's a stunning shift when you consider how successful the encoder-decoder paradigm was. But if we unpack the reasons behind the shift, it really comes down to the brutal realities of hardware and scaling.
Several factors converge to make decoder-only models the ultimate winners of the scale wars. Let's go deep into those factors because understanding why this shift happened is critical if you're deploying AI today.
Definitely.
The first one is simplicity and scale,
Yeah.
but it's more than just being easier to build, right?
Much more. Think about the physical hardware reality. An encoder-decoder setup has two different stacks of layers and two different types of attention mechanisms running.
Okay.
When you're engineering a system with hundreds of billions of parameters spread across thousands of GPUs, moving data between a separate encoder and decoder creates a massive traffic jam.
Ah, so it's a communication bottleneck.
Yes. The communication overhead between those two distinct blocks is a nightmare to optimize.
But a decoder-only model fixes that.
Right. A decoder-only model has one single stack of layers running one type of attention. It's a single, continuous highway.
That architectural simplicity makes partitioning the model across thousands of GPUs significantly easier, doesn't it?
Exactly. It streamlines the training pipeline, the backward passes, and the memory management. You aren't constantly routing traffic between two different halves of a brain.
You're just pushing data straight through a single pipeline. It's the ultimate software engineering principle: reduce complexity to maximize scalability.
And that ties perfectly into the second factor, the unified input-output structure.
Right. In a decoder-only model, there's no structural difference between the prompt you type in and the answer the model generates.
It's all just one continuous sequence of tokens.
The model simply reads your prompt using its own self-attention and then just keeps going, predicting the next token in the sequence.
You don't need a dedicated encoder to process the prompt because the decoder's self-attention handles the context gathering just fine.
The prompt tokens attend to each other, and the generated tokens attend to everything that came before them in one seamless stream.
Exactly.
But wait, what about the translation issue? We just spent all this time talking about how cross-attention was explicitly designed to map the context of one sequence onto another.
It's a great question.
How do decoder-only models pull off complex translation or summarization without that dedicated mathematical bridge?
That brings us to the third and perhaps most mind-bending factor from the sources: emergent capabilities.
Okay, lay it on us.
It turns out that when you scale a decoder-only model up to a massive size, feeding it terabytes of data and throwing unimaginable compute at it, it implicitly learns how to do what cross-attention was explicitly engineered to do.
That's wild. We engineered this incredibly specific, beautiful mathematical bridge between two sequences, and then we realized that if we just build a big enough single-sequence model,
It builds the bridge itself internally. If you prompt a giant decoder model with "translate this French text to English," its self-attention layers are so vast and complex that they essentially build an internal alignment mechanism on the fly.
and that realization led to the death of the old pre-trained then fine-tuned workflow.
Yes. Decoder-only models brought us the era of in-context learning, where you just show the model a few examples in the prompt and it learns the task instantly.
So is cross-attention just a relic of the past? Like a stepping stone we don't need anymore?
Not at all. We should be very clear here. Cross-attention is definitely not dead.
Good to know.
While it may have been phased out of pure text-to-text language modeling, it is currently experiencing a massive renaissance in another field entirely.
The multimodal renaissance.
Yes.
This is where cross-attention truly flexes its muscles today. Because when you're dealing with text, a decoder-only model can handle the sequence.
But what happens when you have two genuinely fundamentally different types of data?
Like vision and language, you can't just mash raw image pixels and text tokens into a single sequence easily.
Exactly. You need a dedicated bridge. And cross-attention is the perfect battle-tested bridge for that exact problem.
Let's look at image captioning as an example.
Sure. You have a vision encoder, usually a vision transformer, or VIT. It takes an image, chops it up into a grid of little patches, and processes those patches into vector representations.
That's your encoder output.
Right, and then your language decoder kicks in. It wants to write a caption.
So it uses cross-attention to look at the image.
Yes. The decoder's query asks, based on the text I've written so far, which specific patch of this image should I focus on next?
And the image patches act as the keys and values providing the answer.
What's fascinating here is how literal this mapping becomes in multimodal models.
Literal in what way?
If the decoder generates the word dog, the cross-attention weights spike on the specific image patches that contain the dog's fur and face.
Oh, wow.
If the next word is running, the attention shifts to the dog's legs or the blurred background indicating motion.
The model is literally grounding its language in visual perception.
Yeah.
And cross-attention is the mathematical mechanism making that connection possible.
Look at DeepMind's Flamingo model, for example. It's an incredibly powerful implementation of this.
What did they do?
They took a massive, already trained language model and completely froze it. They didn't change its text weights at all.
Okay.
Instead, they just inserted new cross-attention layers into it and hooked those layers up to a vision encoder.
It's an incredibly elegant engineering solution. You preserve the massive compute investment of your language model, all that world knowledge it learned during training, while augmenting it with new senses.
Suddenly, this text-only model has the ability to see, all because cross-attention provided the perfect translation layer between the visual features and the text processing.
And it's not just vision. OpenAI's Whisper model does the exact same thing for audio.
Right?
If you've ever used a tool powered by Whisper and watched it generate a perfectly timed transcript, you are watching cross-attention at work.
It uses an audio encoder to process the raw sound waves into a spectrogram, and then a text decoder uses cross-attention to align those spoken sounds with written words.
It handles accents, background noise, and varying speeds effortlessly because it can dynamically scan the audio context, just like that UN interpreter we talked about earlier.
It really is the ultimate interpreter between worlds, whether it's translating French to English or connecting the eyes of a vision model to the mouth of a text generator.
Cross-attention is the fundamental architectural bridge that makes cross-domain communication possible.
And for you, the software engineer, building these systems, understanding this mechanism is crucial.
It's not just about knowing the math.
No, it's about understanding the hardware and compute trade-offs. When do you use a pure decoder-only model for its sheer scalability, simple pipeline, and massive context window?
Right.
And when do you need the explicit, structured bridging power of an encoder-decoder with cross-attention, managing the caching of those keys and values to efficiently map between completely different data modalities?
Making the right architectural choice defines the performance, cost, and capability of your application.
Exactly.
I think that perfectly encapsulates the journey we've taken tonight. We started with the UN interpreter, looked at the matrices jumping around to translate Japanese and German,
We explored the massive compute bottlenecks that drove the shift towards simplified decoder-only text models.
and finally, watch cross-attention find its true calling in the multimodal future.
It's a great example of how architectural patterns in machine learning evolve. Sometimes they're replaced by sheer scale, and sometimes they're repurposed to solve even harder problems.
Absolutely. And that leaves us with a final provocative thought to chew on before you get back to your code.
Oh, this is a good one from the sources.
If cross-attention is essentially giving an AI the ability to perfectly align to completely different realities, like sight and text or audio and text, what happens when we start feeding it data humans can't naturally perceive?
Think about that.
Imagine an encoder processing raw radio frequencies, seismic waves, or complex genome sequences, and a decoder using cross-attention to translate that data directly into natural language.
It could reveal patterns we can't even fathom.
Exactly. Cross-attention might end up being the translator for languages humans haven't even learned how to speak yet.
It's something to ponder while that build finishes compiling.
Definitely. Thanks for joining us on this deep dive. Keep building, and we'll catch you next time.